Welcome to Chemistry Travels. So today we are going to look into the topic solution concentrations. So we all do perform chemical reactions in our laboratories, right? And when do we say that the chemical reaction has taken place? It is when the reactants, they can break the existing bonds or they can make new bonds to form the products, and we say that a chemical reaction has occurred, right? Now the reactants that I take is basically matter. And matter do exist in three different forms, that is gas, solid and liquid. Of course there is a fourth form, plasma, but let's just consider the first three for time being. Gas, solids and liquids are the three different forms in which my reactants can exist. So my reactant in either of these forms can react together to form the products. If I consider the case of gases, we have reactions like hydrogen gas and oxygen gas that reacts to form water. That's possible in case of gases. You can react them provided you give them the correct ambient conditions like temperature, pressure, everything. When it's applied, you can get the product for when you react gases together. And if you consider the next state, that is solid. So calcium carbonate is one such solid. So calcium carbonate is a reactant that exists in the solid form, and if you want to make calcium carbonate to undergo some reaction, we can heat them. And what happens during heating of calcium carbonate, which is limestone, if you heat limestone, the thermal decomposition occurs, giving rise to calcium oxide and carbon dioxide gas. So it is possible to react a solid. Let's consider another solid. This is a solid salt, silver bromide. So if you take silver bromide and put it in the light, that is, you are making it to undergo a photo degradation. So in presence of light, the silver bromide will undergo a photo decomposition to form the products. Metallic silver as well as bromine is being formed. So reaction is possible in the case of such solids also. Now consider that you have two other solid salts. One is sodium sulfate and barium chloride. So these are two, a sodium salt and barium salt. We are mixing together sodium sulfate and barium chloride. We mix together, you put them in a beaker, mix them well. Do you think you're going to get any products like this? No, it's not possible. You mix them, you apply heat to them, you apply some pressure to them. You're not likely to find any product being formed. So what do you have to do in such cases? Not all solids will react together in its original solid state, which means that you will have to convert them to some other form, that is to a liquid state. Salts like these, for example, sodium sulfate and barium chloride, if they have to form the product barium sulfate and sodium chloride, this barium sulfate is a white precipitate that we observe. If that has to be formed, this solid reactants that I have should be converted from their initial solid state to a liquid form, and this is what we mean by making solutions. So many of the reactions that we perform in our day-to-day laboratory experiments, they need to be converted from the solid state to a liquid state. That is, a solution has to be prepared out of them for the reaction of such reactants to occur. Okay. Of course, we do have certain solids that can be just mixed together, and maybe by the process of mechanical milling and all, just simply by mixing everything together, you get the product. There are reactions in solids where they just simple mixing also give rise to product, but we do have certain other salts like these that needs to be converted to a solution state before making them to react. Okay. Now the solution that I prepare will be composed of two major components. The first component is the solid, or it is the substance or the material that I use for making the solution, and that is termed as a solute. It is the solute particles in solution, which is the solid material. And the second thing is you need a medium. You need a medium in which the solid or the substance can be dissolved so as to form my solution, and this medium is termed as a solvent. And solvents can either be aqueous solvents like water, or they can even be non-aqueous solvents. So we do have certain chemical reactions where you would have to dissolve your starting material or your solid material in some organic solvents like ethanol, acetone and all, so as to form the solution and perform the reactions. Okay. And the second thing is, the next question is, how much of solid or how much of solute is needed, how much of solvent is needed to make the solution. You can't just simply be adding as you wish. You can't just keep adding so much of solid and little bit of solvent, or too much of solvent, little bit of solid. So there should be a correct proportion or correct concentration in which you prepare your solution for the reaction to occur. It is something very similar to making your tea or coffee at home. When we make tea or coffee, there should be a correct composition. The right amount of water and the right amount of coffee powder or tea powder has to go in to get the perfect tea or coffee, right? Same goes with chemical reactions, where my solution should be in the right concentration. For some reactions you might need a dilute solution, for some you would need a concentrated solution. So depending on the reaction, you would have to alter the concentration of my solution. And how do I measure the concentration of a solution? How do I know to what extent of solution should be added? What concentration of the solution should be prepared? And to know that, we have 4 different terms that can be used to express the solution concentration. So solution concentration can be expressed either as mass percent or as mole fraction, or maybe as molarity or normality. This is the one that we commonly use in reactions, or it can be also in terms of molality. Now we look into all these 4 one by one. And here we have the first form of expressing solution concentration, which is mass percent. So mass percentage is simply the mass of solute divided by the total mass of the solution, and since it is in percentage, so you have to multiply it by 100. So if I say that I need to prepare 2% Ki, that is mass percentage of Ki is given as 2%. I am supposed to prepare 2% of potassium iodide. So potassium iodide in terms of mass percentage is something that we very commonly prepare for organic reactions in our organic laboratory experiments. Okay. So if I say 2% Ki, I simply mean to say that 2 grams of Ki has to be dissolved in 98 grams of solvent. That is, a total of 100 grams of the solution is being prepared, out of which 2 grams would correspond to my solute Ki, whereas the remaining 98 out of that 100 would correspond to my solvent, 98 grams. Now, depending upon the solvent, you can convert this grams to volume also based on the density of the solvent, and you can just easily measure the solvent in terms of volume rather than putting them in weight form, gram form. So all you need to know is the density of the solvent. For example, if you're having water, water does have a density 1. So since the density of water is 1, we can just say that mass of water will be equal to volume of water, right? So instead of 98 grams of water, I can also take 98 ml of water. It is the same. So 2% Ki can be simply prepared by adding 2 grams of potassium iodide salt into 98 ml of water, and the resulting solution that we get would be 2% Ki. Okay. The next term is mole fraction. Mole fraction is a term for representing solution concentration in terms of moles of the particles that are present. So mole fraction, it is basically the fraction of moles of a particular component. You would have 2 or more components in my solution. Like if I am dissolving A and B together, my solute A and my solvent B is being mixed together, means the mole fraction of my A, that is mole fraction of solute, would be equal to number of moles of solute particles, how much of solute particles are present in terms of moles, divided by the total number of moles in the solution, that is the contribution of both my solute as well as my solvent together, that is the denominator. So basically it is a fraction in terms of moles. Now if as I said, I have 2 components, A, my solute, and I have my B, which is my solvent, then I can find the mole fraction in terms of either the solute or in terms of my solvent, and the mole fraction is represented by the Greek letter chi. So chi A is number of moles of component A divided by the total number of moles, that is from both A and B, that is Na plus Nb. Now if I have the mole fraction of component B, if I need to calculate, I can say that chi B equal to number of moles of component B divided by total number of moles, that is from A and B, that is Nb by Na plus Nb. And the value of mole fraction, it lies between 0 and 1. So, and all together, the mole fraction of both the components together would be equal to 1. The total mole fraction of my system, of my solution, should be equal to 1. So, if you know the mole fraction of one, you can just find the mole fraction of the other without using the formula also. Just 1 minus the mole fraction of the first component will give rise to the mole fraction of my second component. Okay. And the next two terms we consider for representing the solution concentration are molarity and normality. Molarity is given by capital M while normality is represented by capital N. Now molarity, it is the number of moles of solute that is present in solution divided by the volume of my solution in liters. And number of moles of the solute can also be represented as mass of solute by molar mass of the solute. So molarity can also be written as mass by molar mass of solute. Whole thing is divided by the volume of solution in liters. So how do you prepare solutions if the molarity is given? So for example, let's say you are asked to prepare 5 molar NaOH solution. Okay. If we are asked to prepare a 5 molar NaOH solution of 1 liter, 5 molar NaOH solution is to be prepared, means you don't know how much of NaOH is to be taken. So NaOH are pellet form, they are solid pellets. So you don't know how much of those pellets, how many of those pellets or what quantity of NaOH is to be taken for preparing the solution. And for that we use the equation of molarity. So 5 molar is already given. That is equal to the mass of solute that is to be taken, that is to be present in the solution, which we don't know. Let's say that some X value divided by molar mass of NaOH is a known quantity and we know that it is approximately equal to 40 grams for NaOH, right? And the volume of the solution that is needed, it is told that we have to prepare 1 liter. So it is 1. Now to find the value of X, just cross multiply and you will see that you need 200 grams NaOH for preparing 5 molar NaOH solution. And now once you take this 200 grams in your standard flask, what you have to do is make it up to 1 liter. That is the solution solvent that is being added is water, means then 200 grams of NaOH is taken in my standard flask and it is made up to 1 liter by filling with water up to 1 liter, the marking. And the solution that we get in that way would correspond to a 1 liter solution of 5 molar NaOH. In this manner, you can prepare any solution that you are asked to prepare. Okay. Now, if it is 500 ml, so accordingly, you have to convert ml to liter and use the same formula. So, you will get the amount of substance to be taken. Now, this concept of molarity is a temperature dependent term, okay, because molarity involves volume of solutions and we know that volumes change with temperature. Since volume changes with temperature, we can say that molarity also changes with temperature and it is a temperature dependent term, okay. Now, this concept of molarity can also be used to prepare new solutions from existing solutions. That is, if you already have a solution of known concentration, you can prepare from that solution, you can make up other solutions of different concentrations and different volumes. Say for example, I made NaOH, now I have made a 5 molar NaOH 1 liter and now I have this with me. Now I am asked to prepare 2 molar NaOH solution, okay, of some 100 ml. From this 5 molar NaOH, I can actually prepare the 2 molar. Instead of going for this molarity part equation and preparing a separate solution, from the existing, I have already prepared a 5 molar NaOH 1 liter solution with me. So, from that itself, I can prepare the next 2 molar NaOH 100 ml solution. And for that, we use the concept of dilution law, which is given by M1V1 equal to M2V2. So, M1 would be the solution concentration that I am already having, the solution that I have already prepared, the known concentration solution I am having. V1 is how much of that is to be taken, how much amount, how much volume of this already prepared solution is to be taken for preparing the next solution that I have to prepare. So, we don't know how much is to be taken and that is what we are going to calculate. Now, M2 is the concentration that we have to prepare, that is 2 molar NaOH, and V2 is how much of that is to be prepared, and it is told that 100 ml of 2 molar NaOH is to be prepared, means M2 will be 2, V2 would be 100 ml. So, accordingly you can find out how much volume of this 5 molar initial solution is to be pipetted out and that has to be made up to 100 ml for forming the next 2 molar NaOH solution in 100 ml. Okay. So this dilution law is helpful in making up solutions, in diluting or concentrating an existing solution of known concentration. Okay. And the next term is normality. Now it is very similar to molarity, but mostly in case of acids and bases and all, we use normality instead of molarity. And normality is number of gram equivalents of my solute particles divided by the volume of solution in liters. So instead of number of moles, here we are taking gram equivalents, that's the only difference, and number of gram equivalents equal to mass by equivalent mass. Instead of the molar mass, now it is the equivalent mass that we consider for my solute, and equivalent mass is simply molar mass by N. And this N value, if it's the acids or bases, I can say that this N value is the number of replaceable H plus ions in acids or OH minus ions in case of bases. But if you have some other salts, it is basically molar mass by valency. But in case of acids and bases, this N value will correspond to H plus ions and OH minus ions in the corresponding acids and bases that I am considering. So using these formulas, I can calculate the normality of my solution. Like acids and all, HCl and all, we say 5 normal HCl, 10 normal HCl. In that manner, we can see. So these are the two different ways of representing solution concentrations, and these are the ones that is commonly used in our daily experiments or in titrations and all, in acid base titrations or in some synthesis reactions and all, we use molarity and normality. Okay. And finally, we have the last term for representing solution concentration, which is molality. It sounds similar to molarity, but this is molality, L-I-T-Y, and unlike the previous one which was represented by capital M, molality is represented by small m. Okay. And molality corresponds to the number of moles of solute divided by mass of solvent in kg. Previously, we were dividing the solute moles by volume of solution in liter, and in case of molality, the number of moles of solute is divided by the mass of solvent in kg. So we consider the mass of the solvent. Now, number of moles of solute can also be represented as mass by molar mass of solute and divided by total mass of the solvent in kg is there. So if you are asked to prepare a 5 molar solution, so earlier it was 5 molar solution, now it is 5 molar solution of NaOH in some 1 kg of solvent. So all you have to do is you have to find out how much of NaOH is to be weighed out to prepare a 5 molar solution of NaOH. So for that, 5 equal to, you don't know the amount that is to be taken, divided by the molar mass of my solute for NaOH, it is 40 grams. So into this 1 kg, whatever I am having, that kg. So conversions I would have to do because molar mass is in gram and my solvent mass is in kg. So accordingly, you will have to make everything in the same unit, and then you can get the value of X. So you will find out how much of NaOH is to be taken, and accordingly, once you take that much amount, you would have to add 1 kg of the solvent. So like I told previously, this weight can be converted to volume if you know the density of the material. If it's a water, then its density is 1, so 1 kg, and so accordingly you can take 1 kg can be equal to 1 liter, right? So you can just add 1 liter of water to whatever amount you get if it is water. If it's some other solvent, then depending upon the density of the solvent, you can find out what that mass corresponds to in terms of volume and prepare the solution. Okay. And finally, this molality, unlike molarity, this is a temperature independent term because molality is dependent only on masses and mass does not change with temperature, right? Mass is independent, a term that is independent of temperature. So we can say that my molality is also a temperature independent term. Okay. So these are the 4 different ways in which you can represent the concentration of a solution that is to be prepared for conducting experiments or conducting chemical reactions. And I hope you understood whatever has been discussed today. Thank you so much.